Okay, good morning everyone. Let us begin. Our speaker today is Jamerson Bezerra from Toruń, the Nicholas Copernicus University, and he will talk about geometric aspects of horseshoes in higher dimensions. Please, George.
Thank you, Alan, for the invitation, and thank you everyone to be here. It's a great pleasure to be back to Warsaw. That's my second time that I have the opportunity to speak here, and every time that I'm here in the city is very lovely. I'm enjoying a lot of period in Poland, and also it's a good part of that. I visited the city many times, and I always enjoy in different seasons, so which is a very good indication that I really enjoy the place. Today I'm going to talk about a very, very classical subject, which is the geometry of horseshoes. And this, I mean that by classic, I mean that this is a theory that has been developed in the last 60 years or more even, and this is in the core of the hyperbolic dynamics. And so I will try to focus in this talk will be 90-minute plus, and I will try to focus in the first part to try to give an overview. What's my view of the theory, and for those that are very familiar and experts in the subject, I know that there are a few here in the audience. I hope that I don't lose much of your interest. In the second part, I will be a little bit more technical, and I will try to discuss a little bit what I've been working on in the last couple of months, and try to give a little bit of the ideas behind it, which is in the same object. So, the same content. So, what is the setting that I would like to discuss here? So, the main base of study is the space of the homomorphism in a smooth compartment for dimension closed, so I don't assume that have any border, so M for me is smooth, compact, manifold without border, not right. I'm saying. And I denote quite frequently by div of M the space of CR, the homomorphisms. On M. And what I'm going to discuss is properties that are that's the main object of study in this discussion today. And what I'm going to focus my attention is a subset of the class of the homomorphism, which are those that have some very well-established chaotic behavior. I mean, in all of the sense that you can imagine, for example, positive entropy, exponential separation of the orbits, and all of that, and those are the horseshoes. So let me start with the definition, which is the main definition that I'll be giving in this talk. So a horseshoe, and for that I need a couple of lambda containing is for a diffeomorphism F is a compact F invariant set satisfying, and so there is a list of requirements that a set needs to satisfy to be called a horseshoe. The first one is that lambda is hyperbolic. And for that I mean that, in simpler terms, the tangent bundle over lambda can be splitted into invariant subbundles, continuous, with fixed dimension. So the dimension I denote by star. Such that, so what you see locally around a point in the tangent space is the following picture, that you have a contraction of this, one of the subspace, and you have an expansion along the other. And I do assume that I have a non-trivial splitting, meaning that I don't have contraction only or expansion only. That's the basic first property. So this can be put analytically in the following way. There exist constants such that when you look at the derivative, you restrict to es of x, you contract exponentially fast, and you look at the derivative along the unstable direction, you expand exponentially fast. So you can put it like that. So the second requirement that I would like to ask on my set lambda to be a horseshoe, it's more of a topological nature, and I would like to assume that lambda is totally disconnected, and non-trivial. Meaning that it's not only finitely many periodic orbits, so you have some interesting dynamics going on, which could be exactly in this situation. If I don't assume that, you could have a fixed point and you will still have all of these happening, a hyperbolic fixed point. So the third one is more of a dynamical nature, and I would require that lambda is locally maximal, or equivalent, it has a local product structure. And for that I mean that there exists a neighborhood such that you can recover lambda. So lambda is exactly the set of points that never leaves this neighborhood by your diffeomorphism, forwards and backwards. And as I said, this is equivalent to have a property called local product structure. So assuming these conditions, what you see locally around the point when you look at the horseshoe is a picture like that. And I'm drawing these lines intentionally because I would like, if this is a point x, these transversal lines are the leaves of the stable and unstable laminations, which are one of the most important properties that a hyperbolic set with these properties have. Hyperbolic set have. So you have the stable leaf.
I have a question.
Absolutely, please.
Question about point 2.
Yes.
This part totally disconnected. Are there examples?
Yeah, that's I'm going to enter.
Okay. All right.
Give me 5 minutes and I will try to put you some examples in your mind to have the picture exactly what I would like to discuss. Okay, so, but just to emphasize that this is a very important property of horseshoes, that for each, or hyperbolic sets in general, for each point x that you pick, you have a pair of transversal laminations, stable and unstable one. So you have the unstable. And by lamination, I mean that it's not really a foliation, but these guys vary continuously with the point x around points in your horseshoe. So that's the picture that you really see in the manifold, not in the tangent space. Locally, horseshoes are like that. So let's enter in this. Let's discuss a few examples.
But when you say it's not foliation, so what is this lamination?
So horseshoe, by the fact that are totally disconnected, it's a set that does not contain open sets. So you don't see locally a foliation box that is diffeomorphic to some region of Rn where the leaves are preserved. So what you see, it's a picture.
Okay.
And for that reason, you use lamination.
Also, you said that this follows from property 1, so why do you call it property 3? There must be something additional.
So
the locally maximal.
The picture is a consequence of property 3. So this fact that you have this product structure, that you have the horseshoe is exactly the points in the intersection of these lines. So what I'm drawing here is this are the intersections of the stable and unstable lamination. And these intersections are exactly the points of the horseshoe, locally.
So local stable and local unstable from those points, they always
Intersect each other.
inside lambda.
Inside lambda, that's the main
So
property.
That's
Okay,
product structure.
let me clarify that. Thank you for point out that the third property is equivalent to say that for each pair of points x and y, if you look at the stable and unstable lamination, they intersect each other transversally. Moreover, these intersection points lies in the hyperbolic set. And that's the reason that I'm saying that that's the picture that you see locally. And sorry for the confusion. Okay, so, and that's a consequence of tree. So, examples. So first, let's discuss what, and that will clarify a little bit the concept of horseshoe. What is not a horseshoe, but has the first property? I will draw your attention for two classes of examples that are open, extremely important for the hyperbolic theory, but does not fit in the category that I would like to discuss. The first one in this discussion are annals of diffeomorphisms. And the model for this kind of diffeomorphism is given by, if you pick up S, L, and Z matrix, so you have an action in N, and we are assuming additionally that there is no eigenvalues in the unit circle, so you have a hyperbolic matrix. So this induces an action, we can induce an action on Tn. So you have naturally a map from Tn to Tn that for each point or class of each vector you have a. And this is the torus is a hyperbolic set, so it fits in the first class. It's important example in hyperbolic theory because they are stable under perturbation. So the fact that the whole torus is a hyperbolic set, if you perturb the map in the torus, you still have that the whole torus is a hyperbolic set. However, trivially does not fit in the second point because it's not totally disconnected. But what you see in the torus is that for each point you have a pair of lamination as well, but that covers the whole torus. They are really foliations. Foliation, not laminations, and that's what I would like to emphasize the difference. The second class of example, which is remain open, remain stable under perturbation, the condition that the fact that it's hyperbolic comes from a very trivial case, and that's where the no wonder is set. If you don't know what is, doesn't matter, but I'm going to assume that the set of periodic orbits of your system is finite. We have only finitely many. All of them hyperbolic. If you look at the derivative in the correct power, what you see is a hyperbolic matrix. And the stable, unstable leaves around, that always exists by Hartmann-Grobman theorem, lives around points, in the points, centered at points in this finite set, intersect each other transversally. So, in this case, what you see, it's a picture like that. So, I have a nice example here. So, I think the torus is each one of these points is a hyperbolic set itself. But what you see in the manifold, it's a picture like that. It's an example of a situation where this happens. You have here contraction, expansion, contraction, and here you have expansion, and here you have contraction. So all of the points are hyperbolic, all of them, and you have transversal intersection of all of the stable and unstable manifold. This is called Morse's male diffeomorphism. Of course, Morse's male diffeomorphism does not contain a horseshoe. You cannot have a compact invariant set besides the set of periodic orbits that gives you the whole dynamics of the system. It's kind of trivial, have zero entropy, so that's not the system that I would like to discuss, and for that reason I'm putting no trivial. Nevertheless, this is still stable under perturbation, so I need to consider that these kind of maps are inside of space of diffeomorphisms. So I don't expect horseshoes to be dense, for example, because you have Morse's male diffeomorphisms. So the second class, now let's discuss what is a horseshoe. Okay, the first one, it was introduced by Zmeil in the 60s, and it's quite simple. It is a quite simple aid to picture it. So it's given by a linear map even. So I give you a square. So what I'm going to do is to give you the process of construction of the horseshoe. So I can apply a linear map that contracts in the horizontal direction and expands this square in the vertical direction. And what you see after that is a tall vertical strip. So what I'm going to do is to bend it. And for that reason, there is this name horseshoe. It's only because what you see, because of this example, basically. And that's what you see after one iteration of the map forward. Backwards, what you see is a picture like that. And if you keep iterating the square you serve as, I should put U here, sorry about that. That's the maximal property. And if I keep iterating the U, which is this square, what I'm going to see is the horseshoe. So the first stage of the construction are these 4 little squares. If I keep iterating, what I see is 16 squares. And what I see then, it's a product of 2 contour sets. And these lines of intersection are exactly the points of the horseshoe. So as you can see, it's totally disconnected. You have really a product of 2 contour sets here in R2. And it will have the hyperbolic structure because I intentionally put some contraction and expansion to define this set. If you see, you can do it linearly, even though my picture is not. If you do it linearly, the stable and unstable lamination, it will be horizontal and vertical. And this feature remains stable under perturbation. You need not linear anymore, no longer does not need to be linear, but you have some feature like that, and that's the reason that you see a horseshoe. But you can say that's very artificial. You pick a square. But first of all, is that this artificial construction works in any manifold of any dimension. It's local. I only need a tiny little disk to construct a horseshoe. But I think UMK itself, the end of the 19th century, the beginning of the 20th century, you realize that the complexity of many systems lies in the existence of a horseshoe in your system. Even though they didn't use these words exactly, what he featured was a phenomenon which starts very simple on you have a fixed point, for example, and you have some unstable, because you have a fixed hyperbolic point, you have stable and unstable manifolds around it. These are CR leaves. And what he pictures is the situation where these guys comes back to intersect each other. This is called a transversal homoclinic intersection. Even though you have this fancy name, what does it mean? Just that these guys come back intersecting each other. And if you try to do what happens with this picture after a few iterations, you will start to see a situation like that. You see a horseshoe. And if you don't believe, try to picture what happens with this tiny little rectangle around this table. If you start to iterate forward, this rectangle will be contracted in this direction, but you expand in this direction. So what you see, maybe you need to wait a little bit. Exactly this picture. So horseshoe appears in nature, let's say. They appear naturally in many systems, and for a long period of time, people start to wonder if this is how frequent in the space of diffeomorphisms horseshoe are. But let me point out, before I mention how frequent they appear, let me mention stability. Because that's an important property. As I said, if you perturb a horseshoe, you keep all of these properties. And in practice, what this means is that if you, let me write it, there exists a neighborhood of CR diffeomorphisms of F. F is a diffeomorphism admitting a horseshoe, such that for every G, there exists lambda G containing M, which is a horseshoe for G. Moreover, they have the same dynamics. So meaning that if you look at the dynamics restrict to the horseshoe of F and do the same what is for the horseshoe of G, what you see it's a homeomorphism that makes this diagonal commute. And if G is very close to F, this guy is very close to the identity. So that's what I mean by stability. And so the system locally is the same, unlike if I perturb. So it makes sense to consider properties that are robust. If I can perturb it, I still have the property. And that's what I'm going to focus in the second part of this talk. Okay, I'm going to erase the definition of horseshoe for a minute. No, maybe I can make it a little bit longer. Let me erase these examples. So how frequent horseshoes appear? So how can I put it? How frequent? So as I said, you have the Moses medium, so you cannot perturb Moses medium to get a horseshoe. However, as long as you are outside of the Moses medium, you can always perturb to get a horseshoe. And that was a result from Bezerra. So the diffeomorphisms, there is a catch though. The diffeomorphisms C1 can be decomposed in two open classes which are disjoint and such that the closure is the whole space. So up to perturbation, or you are a Moses medium diffeomorphism, or you are in this other class, which means homoclinic interception. That's the catch. That's the catch. The perturbation technique lies in the closing lemma. So that's the main point here. As usual in this.
What was MS? I didn't.
MS is the space of Moses medium diffeomorphisms that are diffeomorphisms with finitely many periodic orbits, all of them hyperbolic, and transversal intersection between stable and unstable. So basically graphs inside of a manifold where every orbit you'll be attracted to one of the periodic ones. which are the vertices of this graph.
That result is for any dimension.
Any dimension, which is a very breakthrough. So if you start with finitely many periodic orbits and you are far from Moss's mail, you manage to perturb to get a Moreira intersection.
What year was this result? Year, when?
Year.
Approximately.
2010, approximately. So it's not difficult to, I think it's called the birth of homoclinic intersections, something in those lines. So it's a very nice result.
But how does your first example fit into this picture? Like, talk about the anosov.
So anosov, it contains plenty of homoclinic intersections. That's the whole point. So if you pick any periodic point in an anosov system and you look at the stable and unstable manifold, they intersect. The point is that this feature happens everywhere in the anosov case. So in this sense, anosov is already very, very intuitive, this class. So it admits, but is not a single. In particular, anosov diffeomorphism contains a lot of horseshoe, which is represented by the entropy of the system. It's very powerful.
It's here in the circle, and dimension 2 is very short.
Sorry, sir.
In dimension 1 of the circle. In
that-
dimension 2, there is very short theorem, which makes it an
Exactly.
smoothness.
Let me mention that in dimension 1 Moss's value, in the circle you have already denseness of it's quite exactly. So it's quite simple that it does not make sense to discuss, but the result is still true because you have Moss's values and the others. It's quite nice result from one dimensional dynamics. Okay, let's move on. That now I would like to slightly change the topic and focus on geometry or geometric aspects of these guys. Now I will not look at anosov for Moss's diffeomorphism, but only focus on horseshoes. Okay. To correct, draw this picture of the literature, I should start in dimension 2. That here, many things are very well established, and they started in the late 80s, 90s, and the 70s, late 70s, 80s, and 90s, and a lot of development here in this area. So let me put horseshoes on surfaces. So basically what I'm drawing here. So that's what you see, and the nice thing, let me just use the opportunity to establish some terminology here. So when you have horseshoes, you have two very nice sets that contains it. For given a point, you have a pair of nice sets, which I'm calling a stable set, which is basically the intersection of the stable lamination of the horseshoe. So how can I write it? And the unstable complex. So I'm all the time drawing these pictures, but what I see here in the horizontal lines is this guy, this stable quantum set. In the vertical line is the unstable quantum set. Around each point you have these guys. And one nice property, topological property of horseshoes, is that the product of these two guys recovers the horseshoe locally. And that's the local product structure, once more. And by recover, I mean that if you pick the correct ball around the point X, you have a homeomorphism of the horseshoe intersected with this ball with the product of these two guys. This is a consequence of the stable manifold theory. I didn't mention, but these laminations have CR leaves, but the transversal regularity is pretty bad, and that's part of our discussion here. And for that reason, just mention homeomorphism here.
Dimension 2 it is not that bad.
That's the point. Unless you are in dimension 2. So in this setting, in dimension 2, you get that, let me put it as a nice property, stable and unstable laminations can be extended to a nice pair of foliations. Meaning that now you don't have only these lines that only pass through points in the horseshoe, but now you have a pair of foliations nicer. They are not invariant anymore, that's a good point here. But by nice I mean that they are at least C1. And
C1 plus epsilon, I don't know.
And for that I need that the diffeomorphism is C1 plus epsilon. Then you can ensure that these guys are C1 plus epsilon prime. A little bit, you lose a little bit in the process. But you have a very nice pair of foliation. What does it mean for this homomorphism? This can be seen as a diffeomorphism. You have a really nice extension of these guys. In particular, geometric properties of these horseshoes becomes trivial in this sense. That in particular, so let me list a few consequences of this fact here. The first one is that these guys are regular Cantor sets, meaning that what you see is that you can map them diffeomorphically over the correct extension to the real line, and what you see is a pair of uniformly expanding maps. When you take the pre-image, what you see is exactly this. And you have the same thing for the unstable maps. And they are very nice C1 plus alpha maps. So these are regular Cantor sets constructed by C1 plus alpha maps of the integral. So K star of X is a regular. And from that property you get everything else, basically, for every X. And for star equals to S. Okay. Example. The Hausdorff dimension of these guys, they coincide with the box dimension, and more importantly, it does not depend on X. I call this property the horseshoe is homogeneous. So for each point that you pick, you have the same geometric aspect. So it doesn't matter the point that you look. The other thing is that, from the nice property of the foliations, and that the Hausdorff dimension of the horseshoe coincide with the sum of the Hausdorff dimensions. The same for box dimension. The box dimension lies between 0 and 1 strictly. It's never 0 in neither one. Things change as slightly if you assume only C1. You could have.
So these are theorems, not definitions.
Those are theorems, but those are classical. I'm recovering some classical results of the theory. If you have any questions about reference, I can give it afterwards of any of these results. For example, Einstein's book recovers all of these results. What I'm saying, it's a consequence of this fact. Wellington, for example, I have a nice article about this. But Palestine is also discussed. Yes, and that's what I was about to write. And does not depend on the context, which is a nice point. The same for box. Lies between 0 and 1, so this guy never has 0 dimension or 2 dimension. By the way, I always comment that if you have C1, you have examples by Bowie that of horseshoes with positive Lebesgue measure. But you can never drop to 0. even if you have C1. This is a nice property. What else I did, before I forget, if you look at the perturbations of your map, you have different horseshoes. You can ask what happens with the house of formation. And this is a continuous. More. It's CR minus 1. That's a result due to Moreira. Moreira obtained this nice regularity using formalism thermodynamic, studying the properties of the transferability. It's quite a nice result, and a little bit under the rug most of the discussions on classical results.
This is for dimension 2.
Everything here is under the assumption that they have horseshoes in surfaces. Now let's start to enter higher dimensions, where things get way more complicated.
Higher dimension, I think it's raw electron conjecture. I did something with Michał Rams and Teresa.
This last one.
No, the sum.
That's I'm going to mention this result, which is a very important one. And let me mention here that the first thing that you have to have in mind when you go to higher dimensions is that these results can be naturally extended to higher dimension if you assume conformality of your system. So everything contracts in the same way, expands in the same way, so it's one dimension in heart. But if you'd like some non-conformality, things get a little bit more interesting. So what survives in higher dimension? Let me call this property star. No longer true. And that's the base of most of the problems in higher dimension. You don't have a nice pair of foliations that recovers your set. So property star is no longer true. And I encourage everyone that is interested in the subject to try to do the following example, where you have a periodic hyperbolic fixed point and you have a two-dimensional stable manifold. And what you do is to look at the transversal intersection exactly in the stable manifold, the strong stable manifold of the hyperbolic fixed point. So in this case, if you choose the parameters of expansion and contraction properly, you see that this example is not even Lipschitz. The stable and unstable laminations. And how can you do this exercise? You pick the holonomy maps. You fix a height, and you look at the intersection of this stable manifold as you iterate with this height. And what you see is that this map is not even Lipschitz. If you choose the parameters properly.
But it's continuous.
It is continuous. It's more than that. It's Holder. So in particular preserves always the positivity of the house of dimension, for example. But better properties than that, no. It's not better than that. Okay, so you have this counterexample. This would be an example of where the property star is not true. But what else is known to be bad in higher dimensions? By the way, this example appears in Palisviani. Article in 94. What else is known to be bad? The house of dimension is no longer continuous when you vary the map. So here I have an example of Bonatti. Early 2000s. Where they discuss the continuity of the house of dimension, and they construct an example like that. It's quite a simple example, very nice one to see, is that you construct a horseshoe linear, but inside a plane. like the one that I drew, I raised the picture, is made horseshoe. And you choose the expansion and contraction accordingly. And you add here an expanding direction. And what they do is that choosing the parameters properly, they are in perturbing this guy to leave the plane, you get an extra dimension here. So they start with something with the house of dimension smaller than 1. That's how they constructed. And they perturb it to get an extra dimension in this direction. The projection here no longer has 0 dimension. And the perturbation will have dimension bigger than 1. So, example, so we write here, for example, of F such that with horseshoe, such that the house of dimension of lambda is smaller than 1, and there exists G as close as you want of F, such that the house of dimension jumps. Have a jumping phenomenon of the house of dimension. And this is with this bad property. Very simple analysis in this example why they get an extra dimension of the projection.
By itself, it is not discontinuity.
It's a discontinuity with respect to the diffeomorphism. So you start with the house of dimension of lambda. You perturb it, and you get something with house of dimension bigger than 1. So there exists Gn converged to F, even in.
Oh, okay, small. Okay, all right. I got it.
Let me just finish this.
No, I understand now. Okay.
It's not even continuous. And to this point, before I jump in, I'm not going to advance much today in these discussions, but I would like to draw this picture of higher dimensions and the complications that appear.
This is in dimension 3, this example.
Dimension 3, but can be, actually the way that they wrote is any dimension, bigger or equal than 3.
Bigger than 2.
Bigger than 3, exactly. Okay, so let me mention a good news which is not in the context of horseshoes, and this is the result 2001 of okay, let me mention, I will say better than to write this one. The result from Felix and Michal, they established the nice properties of a class of hyperbolic sets. Those are not horseshoe, correct me if I'm wrong, they are solenoids, which are hyperbolic sets in 3 dimensions, but they are not totally disconnected. What you see locally, it's a product of a Cantor set and a line. So they're able to construct a nice class of examples where you have good regularity of the house of dimension continuity, for example. And
summarizing, holonomy is Lipschitz, but not on whole set.
yeah,
But where it is not Lipschitz, it has Haldor dimension, which is smaller. We are in that
so,
generally.
so this property survives in a subset, which is enough
Which
to get nice properties.
which has already this Haldor dimension.
Yeah, so you can erase the thing that does not influentiate much the house of dimension. And they still get nice pockets of denominations. And in this spirit that I would like to discuss one maybe technical, maybe not for sure technical result, but I would like to draw your attention to the technique. But it is in this philosophy to focus our attention in a subset which we can extract nice properties of the horseshoe. I will not be ambitious enough to say that the whole horseshoe, even because I can't, have the nice properties, but at least a subset. And I will focus in one property to draw your attention to the technique. And that
The idea belonged to Hasselblad and Schmeling.
that's a good point.
It was not clear it was not written clear what are their conclusions from their particular we understood better the effect when they
Hasselblad have a nice article where he puts as a conjecture that typically, so up to perturb the diffeomorphism, house of dimension of horseshoe, in general hyperbolic sets, it's with local product structure Bayesian sets. It is continuous. That's the conjecture. Typically, if you start with something that you have a horseshoe, maybe this bad example, and you perturb it correctly, then you get something where the house of dimension is a continuity point in this. So that's the main dream, let's say, of the theory right now, is to prove this conjecture. That's not what I'm going to address today, just to emphasize that, but something that could help in this direction. Okay?
You perturb it correctly.
Because you could perturb and still get a discontinuity point.
Right, so I don't understand what is
So-
conjecture.
So the conjecture is, I start with some diffeomorphism F, and I don't know what is, if the house of dimension is a continuity point in this point. I perturb it in a way that I know that this is a continuity point in the house of dimension, meaning that if I start to approximate G, the house of dimension varies well. But if I approximate F, I don't know. So up to perturb, I get. And this seems like a very soft, but it's not because you have counterexamples. It's not very explicit. You don't characterize explicitly what are the bad Fs. But it's a first result in the direction to understand a little bit the typical scenario in the space of diffeomorphisms. And this perturbation, if you guarantee that is CR, better. C1 shouldn't be true, but if you get perturbations as regular as possible, even better. So that's another thing.
But in general, a measurable function is continuous in any point, at any point.
So that's a basic philosophy that you can extract a subset where your function is not so bad. And this is that I would like to focus. In a very quantitative way, because you would like to control the house of dimension, so you need to have some combinatorials in the game.
Yes, there's some terminology about perturbation and dimension. Can you follow this?
I'm not sure if I understand the question. The
This
terminology.
is both ideas.
What Vienna Diaz of the technology for the perturbation.
That they made it.
I see. Now you caught
It's
me
a
there.
term which is well known, but I forgot.
I see. I think I heard it.
We have had here many talks about the boiler, I think. It's
I see.
I'm not sure that it's No,
Blender.
Blenders.
blender.
I'm going to point. I'm not entered because that's a whole word itself, blenders, and I'm going to just point one result that was stated, and there is some preprint, but let me enter now in this third part. And
Orders are described by probabilistic methods. Brownian motions, not by diffeomorphisms.
it's probably a coincidence, but some probabilistic method is going to enter in this part. Now, how bad I'm in time?
You still have 40 minutes.
Okay, that's good. Okay, so let me start to discuss dominated splitting, controlling dimension. Formally, I should write. I would like to ensure the existence of dominated splitting controlling the house of controlling the dimension, not the house of dimension. And for that I need some notation. And some symbolic dynamics, and you get a little bit messy now. Okay, so
you're going away from horseshoes?
no, it's still in horseshoes context. F is a dynamics that has a horseshoe, and in particular, when you have a horseshoe, there is a finite alphabet. A subset, which is shifting invariant of the space of sequences in this alphabet, such that the dynamics in your horseshoe is conjugated to this guy. So you have the shift. And moreover, if you look at the dynamics, this case doesn't matter much. These are those, this is homeomorphism. It's even by Holder, not Lipschitz, but by Holder. Okay, and moreover, if you perturb F and you get some G property, you know that this is stable, so you have the same symbolic dynamics for all of the neighborhood. So the symbolic setting is the correct one to study horseshoes. One of the nice settings to study horseshoes. Okay, and let me introduce some notation. By that I mean the cylinder. Since I mean the symbolic dynamics, I can talk about cylinders, which is the space of sequences in sigma, such that xj belongs to bj for j b n minus 1, where b is a finite word. And I will denote the space, the set, countable set of finite words by A star. So, by the way, I said just a subset. This is a subshift of finite type, has positive as should be by the conjugacy topological entropy. And it's given by transition matrix that determines which symbol I can go further. That's the definition of a subshift of finite type. And for simplicity, I will make many assumptions, but to simplify notation. But if you have any questions about the general result, please ask me afterwards. I assume that you have a full shift. Okay? I assume that 0 is in A as well. It will be useful to have a notation for fixed point, I think. You can call one of the symbols. So the dynamics of the horseshoe is the dynamics of the shift. And I would like to, at this point, to introduce a notion of dimension, which is, it's not the Hausdorff dimension, it's not the first time that it has been introduced, but it's a nice for this context. It's a nice one for this context, which is the upper stable dimension. I will explain the terminology used in a second. Just to emphasize that horseshoes are not blenders in higher dimension. They could be blenders, but they are not blenders in general. But I will mention some of the announced results in this direction involving upper stable dimension. How to define it? So what I'm going to do is to first define a linear cross-cycle induced by our diffeomorphism. So F is a diffeomorphism with a horseshoe, as it's here. And I'm going to define a map from sigma to GLS. The S is the dimension of the stable space of R that sends each point X in the derivative of in the point the corresponding point in the horseshoe, restricted to this stable set. So in particular, this linear cross-cycle, maybe you need to weight a power if you correct you choose corrected the Riemannian norm. I can assume that this happens in the first interval, so it's
But these are not matrices.
this one, no, that's true, but I have a totally disconnected set where I'm defining these objects, and in particular you can choose charts, a system of charts with finitely many of them, and this is the map induced by these charts. So I'm abusing a little bit of the notation, writing as a matrix directly, but I'm composing with the
But
correct
then
chart.
you sort of make it more discontinuous than necessary.
The charts are very good, by the way. So, okay. So let's move. Okay, so this is a property that I would like to focus on. The dimension that I'm going to write it down, it's inspired by the Falconers. Falconers introduced the notion of affinity exponent, a fine dimension. It appears very frequently in the context of IFSs. And it's the equivalent here, but for something that is not locally constant. Something defined like that. So how do we define it? There are several ways. One way to write it down is the following. I look at the set of nodes of size n, and what I do is to, let me just put some notation, I will define A of B as the sup of the A n of x for x in the cylinder determined by B. This is the supremum, which is way smaller than 1 in this case because it's contracting uniformly. And B is a word of size n. Okay. And I look at the set of words and I sum up these quantities to the correct power, meaning that I will look at the correct quantity that gives you 1. If you forget when you look at this function as a function of t, this is a convex function, and it intersects the line equals to 1 in a single point. This is the thing. And you have a limit. This limit coincides with an infimum. It's a nice exercise to see that this has some multiplicativity, these sums. And so you can prove that using this multiplicativity, if you put the word n plus m, you get n times n. And using this multiplicativity, you can prove that there is an infimum for these quantities and it coincides with the limit. And
T times n.
T sub index n. So I'm looking at the set of words of size
might
n.
be different.
It might be, in how quite frequently it will be.
What is A? Oh, A of B is to find the.
So A of B is the sup of the norm of the matrix, which is a very contracting quantity. However, this quantity that you are summing could be huge, is exponentially huge. In this case, that I'm assuming that full shift is the quantity of elements of the alphabet to the power. And so this is the upper stable dimension of the horseshoe. And sometimes I will say that this is the upper stable dimension of the horse cycle, because it only depends on the linear part, as in the affinity exponent for IFSs.
Mine is Hutchins.
Some of the Hutchinsons,
Because he has dynamics.
yeah,
All steps are independent.
it's not. Yeah.
He is more like related to pressure.
Exactly. And you can quantify in nice properties this guy as the zero of the pressure function with some correct geometric potential, which is not in general, because
Which is not.
in general, no, because you don't have conformality.
Yeah, I understand. It's here is supreme. It's not.
Okay, that's the quantity. So what? So we can ask the same questions when you start to vary the diffeomorphism, what happens with this quantity, and what are the properties of this new dimension, for example. And let me put as 3.2. I'm going to mention results, and I will try to focus on different technical aspects. So what are the properties that are known for this function? By the way, this was introduced with this terminology, with slightly different notation by Moreira. Alex Viana, in in a preprint with a lot of ideas but lack formal proofs of the results that they state. But one of the things that they introduce is this quantity, and as a nice replacement for the study, for those that are familiar of you have the Newhouse phenomenon and you have the Moreira cause result in dimension 2, which gives you how to obtain persistently homoclinic intersection when you perturb your diffeomorphism if you have some nice assumption in the house of dimension of the horseshoe. This is the result that's the proposition for this same theory in higher dimensions. And this is the replacement and what properties. The first one is that trivially by this infinite quantity you can see that this is a percent continuous function. So it's table of unity. It's upper continuous. Kind of trivial observation. I don't know if it's always continuous, but I will comment on that. And why is it upper? It's stable upper because it's upper bound of the house of dimension of the stable set. So the house of dimension of ks of x is smaller or equal than the so for every point x. That's what happens already in the IFS case. So if you like the unstable dimension, you will be an upper bound for the stable set, for the house of dimension of the stable set. And that's the only reason for this terminology, because it's an upper bound for the stable dimension. Okay. So what do we know when it's continuous, for example? So here we start to list some results that were announced, but yeah, they need to be published. And one of them is by Moreira. I believe this is early 2000s. And here it's Moreira, Mateus, and here the result is it's not so hard to obtain if we assume that if lambda has a dominated splitting, then there exists a neighborhood, even C1 of f, such that the map that associate each element of this neighborhood, the upper stable dimension, is continuous.
So what is lambda? Lambda is not a horseshoe anymore?
Lambda is a horseshoe for f, as usual, as always. And always assume that you have this context. You have this symbolic dynamic and
But the horseshoes are automatically have dominated splitting.
in 2 dimensions. In higher dimensions, and that's let me define a dominated splitting.
No, I know what is dominated splitting.
No, but it's
I'm
important for
surprised
the
that
discussion.
it's not.
Yeah, I will be important in the discussion, and so it's not to answer the question, but to point this out. What I mean by dominated splitting in this context? Yes, it's true. It always have the stable and unstable splitting, which is dominated naturally. But what I want to emphasize is that the stable direction is also dominated, can be split in 2 directions, and that's the assumption.
Also, so additional splitting on top
Yeah.
of
Stable
the.
and strong stable.
So it's additional splitting to the stable and unstable of the horseshoe. Okay.
strong dominated splitting. I should be more careful, but yes, additionally that we define it. So, by dominated splitting, I mean that the stable direction will be decomposed by a weak stable and a strong stable. And they require, so let me put in the results, because the definition is more general than that, strong dominated splitting with dimension of the weak direction equals to 1. I got ahead of myself before defining the concept. I introduced the result, but that's what I mean. And as dominated splitting, I mean that if you look at the derivative along the weak direction, I should contract less than the other one, meaning that I have a nice exponential, maybe I should wait a little bit so I can see. And since I'm looking at the norm, let me put the conorm. So the least contraction here, it's bigger than the expansion, or the strongest contraction here. Weak stable. So that's what I mean by dominated splitting. I should even put a star in this dominated split because they assume something called sharp splitting, that you have not separation point-wise, but you have the sup of this, the infimum of this is bigger than the sup of this. You can always extract to get this property, so I will not focus on this sharp splitting property. Okay, so if you have dominated splitting, this function is continuous. And what I would like to discuss today is it's a result related with that. It's not new to perturb the homomorphism with a horseshoe to get dominated splitting in a super horseshoe. But what I'm going to focus our attention is the following result, let me state it, and that will be the result that we're going to use the rest of the time to discuss. And this is collaboration with you. And the result is the following. Let F be a CR. The homomorphism. R is any number big or equal than 1. Admitting a horseshoe. Given an arrow, there exists a diffeomorphism CR, which is CR close to F, such that two things happen. And a sub-horseshoe, so it will be a subset with a nice structure, lambda G prime contained in lambda G, such that the dimension upper stable of lambda G prime is close to the dimension of the region of F. Okay. What's the second property? Lambda G admits a strong dominated splitting. Many times in the this situation where you have an extra splitting with one-dimensional center, it's called partially hyperbolic horseshoe with one-dimensional center. It's not partially hyperbolic, it's really uniformly hyperbolic, but meaning that you have an extra splitting with one dimension. And that's what we have here. That's the result. So, in other words, what I'm doing, I start with a diffeomorphism F with some upper stable dimension. What I'm telling you is that I can perturb it without losing much of the upper stable dimension, and then you won't have an answer within the strong stable, strong dominated splitting. In particular, this perturbation will be a continuity point of the upper stable dimension, which is the result that we were discussing before for the house of dimension, this kind of typicality. But without even lose the initial upper stable dimension. That's what I would like to focus our attention on. And that will be a little bit more technical, but I would like to focus on a few ideas. And for that, I'm going to first simplify the maximum that I can to focus in these ideas, the combinatorials, which gets a little bit messier in terms of notation.
But that's only for the stable upper dimension, not necessarily for the actual Hausdorff dimension of
the actual hours of dimension. That's a further investigation. It's a little bit.
It's not like hopeless. It's.
But what we expect to happen that once you perturb nicely, you get the sub-horseshoe, and in this sub-horseshoe they coincide, the Hausdorff and the upper stable dimension. In dimension 3, if the Hausdorff dimension is smaller than 1, the correct way to pose this the claim. That's a question. Let me put it like that because it's not a conjecture. If you perturb it nicely, and you define not the upper stable dimension, but the other you involve the similar values of your map, that's the correct way to measure the Hausdorff dimension. That could be too big, the upper stable dimension. But if you once you perturb it, they should get match this horseshoe.
The dimension of the horseshoe, not just the stable or unstable.
Yeah, but once you have the stable and unstable, what you expect once you perturb it and extract, you get the correct product structure.
But this is again just an expectation.
Not a result. I'm not claiming, but it's reasonable that this is true. But with the correct dimension, not the upper stable, but with the affinities. Singularities, which is the generalization of affinities. Okay, so what's the idea? And how much time do we have?
You have 15 minutes. Yes, 15 minutes.
Okay, so that will be very hard. So let me try to give you some bullet points, hiding a little bit of the combinatorials. Okay, so I'd like to get a dominated splitting. What is the strategy to get dominated splitting? Cone fields. If you have a nice cone field that will be centered inside the other, you'll get dominated splitting. That's our goal. So go construct a cone field. Cx inside this definition. Okay, for x. Maybe not in lambda, but in lambda prime of g. That's the philosophy here. That I can find this sub-horseshoe where I can find this cone field. And what is a cone field? I would like to ask that the way that you define the cone, you get some continuity local. And you can find the cone in terms of directions, not necessarily invariant by your diffeomorphism, and that's the continuity that we require. Or quadratic forms, the way that you prefer. But I would like that when you act by the cone, by your map, you get inside the cone. That's what a cone field means. Okay? And that's our goal. I cannot choose yet, I need some preparation, and the preparation is the part that I would like to discuss now. Let's say that that is the main theorem, and this is the theorem 1. And for correct, put these I need preparation. And that's where I give myself some flexibility, introducing some probabilistic tool in the game. So what I do? I have my set of cylinders of size, of a specific size, let's say n. So for each b, okay, fix n, much bigger than 1, and m is smaller than 1, but it's still much bigger than 1. So everything very large. And I look at the set of words of size n, and I perturb my linear cocycle. Let me keep the notation here just for us to have in mind. And here I'm going to reduce once more to simplify dimension 2 in this table, but it works in other dimensions in this table. And here what I do is consider an angle theta b. Delta is a small parameter, perturbation parameter, and I define a theta bar of x equals to a of x times a rotation, where theta bar just means theta b, just a notation to indicate that I'm doing the same perturbation randomly in each box of the Markov partition. So my horseshoe, when you look at the manifold, you have many boxes inside of this stable manifold. So what I'm doing is looking at high levels of this construction and perturb randomly each one of the boxes. And I'm claiming that I can do that to get dominated speed. That's the main philosophy here. So many, you can find in the literature this called the family of random perturbations. And so I would like to address this probabilistically. So what's the probability to get dominated speed in a sub-horseshoe? For that, an extra simplification is that so if you define the set a whole is a positive parameter of the words, finite words, such that that maximum is approximately whole, the cardinality of this set is O is a small parameter. So I'm going to, the correct way to do what I'm going to do after is to check subwords of the set of words with the correct parameter, where you approximate the exponent upper stable dimension. I'm not going to do that. I'm going to focus only in finite words, and I'm going to erase small sets of finite words without thinking much about the upper stable dimension, but that's the correct way to do it. It's looking at this subset. Okay. So I think for the main geometric idea, it's already the first result, and let me see a way to announce it. So you pick a parameter n much bigger than 1, and I'm going to write it down as n, artificially way to write it, n to the power 15 plus n to the power 18 times n to the power 12 and plus n to the power 15. Huge. N is small, n is huge. So it's an artificial way to decompose a number. And why I'm doing that, I'm going to explain in a while. First, let me fix one parameter more, which is m. Maybe I don't need this m. But I need a subset of words of size n, which is a n of n to 12. This is the set words of length capital N such that, and it will be very clear this in a second, the subwords of length n to the power 12 does not appear twice inside. So the picture is like that. Huge n, I look at small strings of sub to the power n to the power 12 here. If it appears here, it never appears anymore. That's the thing, and that's my nice set of rules. And then once I have that, and I have that my delta is of the order n to the power 10, I think should work, I can define the set of random perturbations, which is minus delta to the power cardinality of A to the power n to the power 12. So I'm going to perturb this construction with n equals to n to the power 12. So I'm going to even emphasize this fact here. And this is my space of perturbations. Remember, each one of the woods here, I'm doing this random perturbation, and that's the result. By a probabilistic-ish like argument, there exists.
So capital N is something large but fixed given f, or?
Once I have f, I can choose capital N as long as you want. And the idea is that later I can approximate the perturbation by this choice of subset of words. By the way, this set of words seems complicated, but it has cardinality, almost the whole cardinality of the whole set of finite words of size n. Because extract subwords, which is tiny, does not change too much. You don't lose so many words in this process. And that will be clear once the result is stated. There exists delta bar such that I need, before choosing the cone, I need control distortion. And it's not bounded distortion, but sub-exponential distortion. And that's the reason of these weird decompositions. I cannot expect bounded distortion without losing many words. But the sub-exponential, yes, and that's what I do. So the sub on x and y of a n of x theta bar after perturbation divided by a n theta bar y, it's sub-exponential. Maybe some constant here that does not depend on n, but here you have a constant, universal constant c, could be here, huge, minus, because it's bounded distortion. But here you have something sub-exponential, and I think you can put here 1/2 with this choice of parameters. That's, I think, no, you can. And if you look at the set of words B that have this property, in this subset, of B in A is star n of n to the power 12, such that this property is true, the cardinality of this set is huge. That's the main geometric property that we require, that I can perturb randomly. There exists a parameter. These are going to have positive probability that this guy is bigger than this guy. Okay. I will not enter much in the details of this property, but let me give the bullet points on why I'm using this bounded distortion property, sub-exponential distortion property. Once you have, now we focus in this set. This is my new set that I'm going to, since I didn't lose much in this process, that's my new set. So my horseshoe have bounded distortion in this sense after perturbation. I forget the theta because now that's what I'm assuming. I can perturb once more. But before that, I am going to do the following simple dichotomy. Even half of that set of words, you have distortion, but it doesn't mean that you have contraction when you act in the projective space. You could have conformality, even though in the word you have some distortion, controlled distortion. And that's bad. So what you do, either half of your words have already some nice hyperbolicity, or half of the words have conformality. And that's where the distortion appears, to control this dichotomy. But once you have this dichotomy, if you have some conformality, you can pre-compose your cocycle with a one in a periodic orbit, which is very hyperbolic. So the second step is to, if a word, in the sense that the derivative of the diffeomorphism in the interrate in this word is very conformal, and this is a very conformal, this is a very precise way of conformality, it's a sub-exponential one. Then the word 0k, once you perturb to get hyperbolicity in the fixed point, you can always do that. This guy is very hyperbolic. Now you have plenty of words that you can construct without losing this k. It's related with the size of b, it's much smaller. So the hyperbolicity is not that big. But once you compose things that are hyperbolic, you remain hyperbolic if you correct the angles. That's the new set of random perturbation, where you use a kind of avalanche principle to control the angles between products of words. Many hyperbolic words multiplied, now the product is hyperbolic, the singular direction is aligned, you can define your cone. So the cone, after this process, is a cone centered in the singular direction of one of the elements of the word, the very hyperbolic that you have. In a very large angle, like pi over 2 minus epsilon. So, since you are very hyperbolic, large cone will be inside of the cone in a controlled way. Once you have your cone, you contract your cone, but you don't know if it fits in the correct place, which is the cone of the next word, because the cone depends on the word that you pick. What you do? Perturb again, to force that, because you have a very large openness of your cone, you can perturb to fit exactly, but not for all of the pairs of words of size n, but for a subset large. So you define a subshift of finite type induced by if the cone goes inside the cone or not. Find the interior. So once you have this set, this is your sub-horseshoe given by this transition matrix. You have to do this very in a quantitative way to not lose so many words in the process. Each perturbation that you do, you lose a few, but it's sub-exponential because of this kind of decomposition. Every time you lose n to the power 12 k, which is the amount of symbols, let's say, to the power n to the power 12, inside sets of words of size k to the power n, which is way bigger. So it's the combinatorial part here that interests. Once you have this nice set of words, you have dominated split, and that's the philosophy here. Sorry about the mess in the end, but that's the overall idea, what I've been doing recently. So thank you very much. Dziękuję bardzo.
Thank you. It's time for questions.
So, this is the claim in the theorem, right? In the second claim, should be a prime, right?
Lambda G prime, thank you. Yes, as a sub-horseshoe.
So, by itself, it doesn't impress me. What's the consequence of these properties? I'm kind of lost.
Okay.
Why is that?
The first one that I mentioned is the fact that you can perturb to get something that you know that is continuous, which is this typicality of dimension. It's not the Hausdorff, it's this upper stable dimension, but you have typicality of the continuity of the upper stable dimension. That's the first consequence that you get automatically. The second one is that once you have dominated splitting, you have the foliations strong stable and weak stable. This weak stable is not unique, but you have at least a unique strong stable foliation, and you can talk about projections in this direction, which is the basic tool to understand the geometry of the horseshoe locally. And once you have that, you can do a few things. It's better than write and say, if the upper stable dimension of your horseshoe is bigger than 1, so it means that when you look inside the stable manifold, you get a lot of overlaps once you integrate the elements of the macro classification. And this kind of picture inside of the stable manifold is where you expect the blenders to happen. And once you have blenders, you can talk about more sophisticated kind of dynamics. For example, you can talk, it's a mechanism of construction.
So these claims lead to blenders.
Leads to blenders. If the upper stable dimension, so let me do the general claim that was stated, but the preprint is available, but a little bit fuzzy. So if the upper stable dimension, this quantity weird that I introduced, is bigger than 1, then, and you have this property, this strong domination, not only you have continuity of the upper stable dimension, but upper to perturbation, your horseshoe will be a blender. So you can perturb once more to get blended. That's a result of Mateus, Moreira, and Silva. It's part of that material that I announced before. So the whole technicality here is to fit in the assumption, to start to construct blenders using this kind of technique again. So that's the first point. You can wonder what happens if the upper stable dimension is smaller than 1 then. So you don't expect to have so many projections along the stable intersecting, but they could still intersect. But that's the part of the things that I start to do, and I'm in doubt. Which is, if you have just few of these guys, and the dimension is smaller than 1, you can perturb it laterally to get disjoint projection. Once you get disjoint projection, you can control the Hausdorff dimension. So this is you can think as a brick to start to, but it needs to be done in such a way to control the upper stable dimension. That's the way that I see it. Thank you.
Maybe there are some questions online. No, doesn't seem so. So let's thank Jamerson once more.
Thank you.
Yeah, that's it for